C'est bon ou pas? Okay. So welcome everybody to this talk entitled Papyrus for Simulation. So today we are going to speak about one tool which is developed in the context of Papyrus. And this tool is basically to take advantage of models to perform simulations. Well, first we will see how this tool is integrated inside Papyrus, what are the challenges that are solved by these tools, and we will try to give you an overview of what is the architecture of the tool in terms of implementation. It will just be general principle. We will see the different basic features that are provided by the tool. So how we can execute model, how we can control model execution, how we can observe value manipulated by the runtime. And we will have a focus on possible extensions and customizations of this tool, especially around these three axes for time support, custom semantics, that means to have a custom execution engine for a particular language. And we will see that we also propose an integration with FMI to perform co-simulations. And the last point will be the roadmap for the next release of the tool. Okay, let's talk about the integration inside Papyrus and the challenges of the tool. Well, as most of you know, probably, Papyrus is a modeling environment, and these modeling environments are the set of tools that are around it that provides basically new functionalities to exploit models that are produced in Papyrus. You have two types of contributions. You have add-ons and customizations. Add-ons basically use the model that is produced by Papyrus to perform simulation, code generation, test generation, and so on. Moka is one of them. And the second kind of contribution that we have is customization of the modeling environment itself. So that means for a particular language, we are going to filter property view, filter the model explorer, change the shapes that are displayed on the diagram to make the tool looks to make the tool to meet the requirements of the engineer that are going to use it. Okay, just for the word, so Moka is for simulation, Compass is for code generation, Diversity is for test generation and formal analysis of model, and Sophia is for safety analysis. Okay, well, the objective of Moka is to provide Papyrus with a model-based simulation framework. And why we provide this is that the model is the primary artifact of your future system. And so you need to be able to evaluate, at least functionally, that what is model is effectively what the system is going to do. And to do this, we provide this execution engine. So basically, you model the system with Papyrus. The system is executed, simulated by Moka, and you have simulation engines that are provided. You have control over the simulations, and the simulations appear on the model. That means you have animations which illustrate where you are basically in the simulation of on the model. So there is a strong connection between both tools. And all the simulation engines that are provided by the base implementation of the tool are based on normative semantics of UML. Okay, let's now get into the architecture of the tool. The tool is basically composed of 4 components, and these 4 components are the execution engines that basically provide interpreter to interpret, simulate the model. You have services that receive notification from execution engines, and these notifications are interpreted by themselves to, for example, control the simulation to debug the simulation, to perform an animation, to produce the traces along the simulation. You have the component libraries, and libraries are basically a set of model signatures, and these model signatures are basically connection to legacy libraries, for example, to do addition between integers, to do I don't know, a concatenation of strings and stuff like this. So you have a set of libraries that helps you to build a complex model without to rewrite everything by yourself. So the tool is customizable in the sense that it provides a set of free extension points that allows you to add new execution engines. That means if you have a language for which you need to write a new interpreter, then you need to contribute to this extension point to provide a new simulation engine. You have the possibility to contribute to a new service, and basically this contribution lets you, for example, provide a new tool for the debugs. That means you will have the opportunity to control the execution in a different way that it is basically controlled by the tool. You can also register a new model library, meaning that if you, for example, need in your model to specify connection to a database and you have an existing library for this, you can contribute to the tool, register this library, connect it to the real Java code that will perform the connection to the database, and so it will be available. Okay. The basic implementation of the tool has 3 execution engines. These execution engines are fUML, PSCS, and PSSM. And they basically implement normative specifications that are produced at the OMG, the Object Management Group, which normalize UML and its semantics. The engines that implement fUML basically make possible to interpret models built with classes and activity model. In addition, we also have an execution engine for composite structure, meaning that in addition to classes, activities, you also have the possibility to use in your model composite structure, and so to use port and connector. We also have another one, which is for state machines, and it provides a way to interpret state machine model. All these execution engines are cumulative, so that means the subset that is supported here is included in this one, and this one is included in this one. So if you use this one, you also have the possibility to use composite structure, classes, and activities in the same simulation model. Well, when you want to contribute to a new execution engines, basically what you do is to extend this class. It's not readable. I'm sorry for that. It's abstract execution engines, but well, that's not important, the name. But basically, it is agnostic of UML. That means if you have a new engine and you want to interpret another kind of model for another language, it's also possible. So Moka is not completely bounded to UML. And basically, what does the basic implementation is that for the abstract execution engines, then we load all register services that will be used to debug, to animate the model along the simulation. Okay, let's talk more about the different services that are implemented. Well, we have two. We have one which does animation and one which does debugging. So basically, they all implement the interface Moka execution listener. And so we know that when a node, for example, is visited, then we perform animation for this node in the animation service. And in the debug service, if a node is visited and this one is in the context of a particular active object that needs to be suspended, then the execution for this particular active object is suspended. we have also, well, a mechanism that allows, at the end of an execution, to properly dispose all the resources that are taken by this service. And this is basically implemented in the dispose operation. Okay, this is a sequence diagram that summarizes basically how the service mechanism is connected to the execution engine. What you have is your abstract execution engines that basically handle a particular execution, and an execution is an interpreter for a particular behavior that is specified in UML. And when you go through a particular node, then it calls a particular aspect, and this aspect triggers an advice, and this advice will notify the abstract Moka service, the services that are registered into Moka. And this will let the services to interpret the event and to perform some behavior that are implemented in the services. So for the animation services, we have such kind of contribution. Basically, we declare a particular marker for each kind of animation we want to perform. That means we can basically have three states. We are animating. That means we are currently executing the node. This node has been visited. This means it already has been executed, or the execution is suspended on the node. We declare all these markers, and when these markers are registered, they are automatically associated by Papyrus to a particular CSS contribution, and this CSS contribution basically defines the style that will be applied to a particular model element at the time it is visited or left. And well, the application of a particular marker on model elements triggers the CSS execution engine of Papyrus, which applies a style that is registered. Okay, well, this is here the basic behavior that is performed by the animation service. So just when node is visited, then this animated marker is applied. When the node is left, then we apply the visited marker, and these are interpreted by the Papyrus CSS engine. We have another contribution through this animation service, and basically this one makes sure that each logical thread that is currently running is allowed to animate a particular set of diagram. That means for a particular diagram, you can select which logical thread is allowed to animate the diagram. So if you have multiple instances of the same object that are all animating a diagram, then you can select the one that you want that will be effectively allowed to make the animation on it. That does not mean that other active objects do not execute the model that is behind the diagram. That only means that the visual rendering of the simulation is only performed by a particular logical thread. Okay, the second service, as I spoke about, is contributing to the debug model of Eclipse. And basically, what we have defined is that this debug service is connected to a particular debug target, and this debug target registers a set of particular threads that are Moka threads that are in UML term corresponding to instance of active classes. And basically, the rendering of this through the Eclipse UI is there. So you can find the process that is currently executing, the different logical threads that are registered, and if these logical threads are suspended, then you have the stack frames that is associated to each logical thread. And if you select a particular stack frame, then you can get a visualization of all values of the attributes of the object that is currently interpreting the node on which the execution is suspended. And this is made possible because we also developed a set of adapters that are able to capture the data model that is behind the execution engine of Moka. So while the basic behavior of the debug service is if a node is visited and a breakpoint is applied on the node, then the logical thread that is currently interpreting this node then needs to be suspended. But it can also be a user request. That means if the user click on pause, then for this particular logical thread that is concerned by the user request, then we suspend the execution. If you click on resume, it will restart the execution as usual for any Java program or program written in another language. Well, when values are created and values are destroyed in the runtime, we register logical threads that are created, or we destroy them if they are terminated. So here is an excerpt of the adapter model that we have set up to make possible the visualization of the data model that is used by the Moka runtime through the Eclipse debug view. Here is a concrete example. That's, for example, for a structured value, that means for an instance of a class in terms of fUML, then where we have defined this adapter, which is actually adapting this value, and a structure value is usually related to a set of feature values that associate properties, UML properties, to their effective values. And for this one, we define a feature value adapter which is able to look inside the real object and make it visualizable through the Eclipse debug view. Okay, this was a lot of theory. Now let's see how the tool looks like and how it performs simulations. Okay, here is a very simple example specified in raw UML. Okay, we have two active classes. These two active classes have an associated classifier behavior. A classifier behavior is just a function. This function is here defined in an activity. It could have been defined using state machine. It would have been the same, but the syntax would have been different. Okay, the principle here is that this class, which has this particular behavior, handle a counter, okay, and when it received a tick signal, then it makes sure that the counter is incremented and then sends a response to this object, which is waiting for its response here. And so basically continue its execution until there, and then send a tick back to this object, which is now waiting on this particular node, and then continue its executions. So it will run as a while loop, but it's an example. Okay, well, the execution of the model that we just saw needs to be configured in the tool, and basically, what we have to do is to declare a launch configuration, as for any Eclipse application and so on. So we create a new launch configuration. This launch configuration points on the UML file containing the model that you want to simulate. You have the element from which the simulation must start. And then you have the choice among a set of execution engines that you can use to perform the simulation. And these execution engines are basically the ones that I presented previously. You have fUML, PSCS, and the other four state machines. You see also different ones here. This is because this screenshot has been taken from the very last version where we have also included support for co-simulation. Okay, and what you will see in the tool when the execution is running is that the diagrams along the execution will have changing colors, materializing the object that is currently under execution, the model elements that have already been executed. This is for the part for the animation. And for the debug, you can see what are the logical threads that are currently running. If the execution is suspended, as in this screenshot, then you can see the values of the current object. You can also control the speed of the animation. Okay. Now what I'm going to show is just a simple application on what I've just presented. So here you can see the two diagrams that were in the slides that implement the exact same behavior that was the one that I just presented. Here, so I have already launched one time. So I will remove this. I can select the launch configuration that I've already introduced in the tool. So you can see that this launch configuration points on the model that needs to be executed. You have a pointer on the entry point of the execution and the selection of the model that needs to be executed. Okay, and hopefully you see that the execution is actually running. Unfortunately, you cannot see everything on the diagram, but anyway. Okay, you can see that it effectively is waiting for a particular tick signal. When it receives it, then it increments a counter. And what I'm going to do now is to add a particular breakpoint on this node, and when it comes back to this one, then the execution is suspended. And if I unfold this and look here on stack frame, look at the context object, I can see the counter value. And if now I release the execution, it will do another step, stop again, and you can see that the value here has changed. So that's basically things that you can do with the tool. Okay, let's now speak about the extension that we have provided to Moka. This is we have simulation engine for raw UML, but now it is you have situations where people need a specific language, use a specific profile, and so we need to have the possibility to execute model with a custom semantics. Okay, we have another axis, which is time support, because usually some system that we are simulating requires time to be taken into account. So we have introduced a time support, and we have also a support for a co-simulation. And basically, the co-simulation principle is that we can import a model from other simulation tool and assemble them in a model, and then simulate them through a master algorithm. Okay, well, for the time support, basically the problem was it was originally not supported into the part of UML that has a formal semantics. So we need to introduce it, especially to to answer to the question that, well, how do I simulate this needs to be done after a specific amount of time. So how we have solved this problem? Basically, we have introduced a discrete event scheduler, which implements a regular discrete event semantics. That means we have a pool of events that are emitted by object executing inside the runtime. These events have a specific date, and a step of the discrete event scheduler is to consume all events at a specific date, and so release the behaviors that are attached to these events. And well, we have a very simple example here. Again, it's not readable, but basically what is specified here is that we have an accept event action, and this needs to be triggered at a specific time, which is the time that is specified here. So basically, you have a first step. The model execution is suspended here, and the time is elapsing. And when this time is reached, then the second step can be done. We register again this accept event action, which means we need to wait for a certain amount of time, and then we can just continue the execution at that point of time. And this is basically the same for the next example. Okay. We also have extension for profile semantics. Basically, it is common to have some stereotype coming from art, from SysML, placed on the model. And then, if they are placed on the model, then they have semantics. And this semantics needs to be reflected in the model execution. This implies that some execution engines that are registered into the tool needs to be extended, or a new execution engine needs to be introduced if no existing execution engine can be extended. And one example that we have is, for example, we have an implementation of the BPMN profile, and this BPMN profile leads us to build process model, and this process model has specific semantics. So we need to build a new execution engine, and as the BPMN profile is very close to what we can find inside activities, and then we define the new execution engines on top of the fUML implementation. So the example here, I hope it will be readable this time. Okay, we have a very simple process. Basically, we produce something here, and here we have orders, and these orders are emitted by clients, and they arrive at a specific rate. Okay, and here we match a specific product to a specific order, and we are going to perform a simulation using a customized execution engine, implementing the semantics of BPMN. And basically what we have added here is, for example, some schemes to illustrate what are the loads of each task that are executed inside this model. Basically, this line, the red line represents the consumption of the product, the raw products that we use to build the product. And this line represents the orders that are accumulating. And what we have just seen here, sorry, it was not readable, but what we have seen here is that orders were accumulating, so we were not fast enough to produce the product that we want. So what we need is to refine our simulation model and add the possibility. Here it's basically a test station that tests the conformance of the products to what is expected. What we need is to add another test session to make sure we are going to accelerate the process of testing the product to make sure that we are fast enough to respond to the different commands that are emitted here. And what we will see next in the video is the scheme that effectively shows that this is the case. Okay, sorry. I tried to click to accelerate a little bit. Okay, so here, the line which is here shows that commands are not accumulated anymore. And the third extension on which we have worked is the extension related to the implementation of support for co-simulations. And this support for co-simulations is needed because whole model cannot be specified in UML. We have model that needs to be specified, for example, using Simulink to reproduce physics law, or in another simulation tool. And we need to be able to import this model and to assemble them, for example, with another control model that would be specified using UML, for example, for the control part, and to connect them through a graph or composite structure and co-simulate them using a master algorithm. And this is basically what we see here, is that this assembly is interpreted by Moka using the composite structure engine plus the master algorithm. And what we produce is a CSV file containing, along the time, all the inputs and outputs that are produced and consumed here. And we are able to display them on a particular diagram that has been implemented inside Papyrus. I have also a video to illustrate this. So it will show how we can import FMUs inside Papyrus. And so FMUs are just packaging for a model coming from other tools that are able to be imported inside Papyrus. Okay, I'm going to accelerate a bit just because I'm running out of time. And just to show you what is essentially. So here you have the imports of FMUs. And basically we can see that they are imported here as part of the model, and they can be dropped after all on the model. So here it's an FMU, which has an entry port and an output port. And we can see later on that it is associated with another FMU, and that we can run the simulation as usual using the same kind of launch configuration. The master algorithm that is coordinating the execution is hidden behind the execution engine. Okay, here it performed, one simulation was performed, and we are going to see the result by importing them. So basically it imports a CSV file, and here you can select the variable that you want to see, and then it produces this kind of graph that you can analyze after the simulation. And if you want the curve to be polished, you need to make the simulation more precise. So you need to reduce the step size. For example, here he moved from 10 to 1. That means we are going to do 1,000 steps instead of 10. And then that you see that you have a lot more points to observe along for the simulation. Okay, let's now talk a little bit about the roadmap that we are going to follow for the oxygen version. basically, what we need to integrate now is our implementation of precise semantic of UML state machines. At the OMG, the initial submission was done in March 2016, and the revised submission will be done in September 2016. So next year, this execution engine, which is an implementation of the OMG specification, should be available. For the debug part, we need to have a full support of fUML on PSCS data model. And for the debug part, we need to enhance the debug mechanism to make sure that we'll be able to control state machines in the same way that we are already controlling activity execution. We have some support for tracing, but this still needs to be consolidated and is not released yet. And this will be probably part of the Oxygen version. For FMI, we need to work on the FMU export part, meaning that we will be able to encapsulate a model produced through Papyrus and execution engine described inside Moka into an FMU and make it importable inside another tool like Simulink. And one other important thing is that we need to be able to plug a new master algorithm easily. And of course, the user workflow is still need to be improved. For the moment, the FMI part is really an ongoing work. Okay, and there is another part which is related to the ease of specifying model execution. This is a work that will be done directly on the Papyrus editor to make sure that it is that we need few clicks to get to a fully executable model. Okay, well, this is not important, that I'm running out of time. Thank you for your attention. And if you have any question, do not hesitate. Yes?
So I guess in the future, if you do some system integration and you have parts that use different simulation engines, do you have plans for like making them into like interact these engines?
Well, what do you mean by interact?
Well, for example, you have one function that is done in like this state charts with signals, and another thing that's in a different format. That's a different engine would run, and then you, for example, send a signal over to the part that is carried off by or interpreted by a different engine, that you can have like them interact.
Yeah. The interaction will basically be done by data. The signal will not be directly transmitted. It will be directly transmitted if we are in model of the same nature. That means if you, for example, send a signal from an activity to a state machine, then this is the signal that is transmitted. But if it's between models that are heterogeneous, then the data that will be transmitted will be concrete data. That means primitive data, integer, real, limited natural, and so on and so on.
So, is there an interface to say like, okay, here's an engine, and there's like a protocol that you can tell the other engine, okay, I want to invoke something in there.
Yes, there is a protocol, and this protocol is defined by the FMI standard, and we rely on this to make sure that different model interpreted by different execution engine can effectively